Okay, in this video I'm going to talk about the Brooks theorem. So this is a theorem in graph theory that gives an upper bound on the chromatic number of a graph in terms of the maximum degree. So I will first give a very rough statement of the theory. So the theorem says that under certain conditions, so he of G, he of graph G is less or equal than delta, the maximum degree of graph G, under certain conditions and with certain exceptions. So this is a general statement. So now I will give some background to explain all these conditions and exceptions. So yeah, so like I need to write here that this is under certain conditions and with certain exceptions. So now so for the background, so let me give the definitions first. So the definition of the chromatic number, so the chromatic number of graph G, denoted by he of G, is the minimum number of colors required to color the vertices of the graph G properly. So and the proper coloring is when any two adjacent vertices that are connected by an edge are colored into different colors. So the situation where the vertices are adjacent and it's colored into the same color, like the situation is prohibited. So now the maximum degree, so the definition, the maximum degree of G is simply the maximum of all degrees of all vertices in the graph. So when V varies by all vertices in the graph. So this is quite obvious definition. And then there is a kind of a trivial, well, it's not completely trivial, but like a simple or an easy upper bound on the chromatic number in terms of the maximum degree. And it says that for any graph G, the chromatic number is less or equal than delta plus 1, delta of G plus 1. Yeah, so I actually made a separate video about this, but let me give here at least briefly the proof of this theorem. So because the main idea would be used in the Brooks theorem. So the idea is to use induction on the number of vertices, right? So induction on the number of vertices in the graph G. Well, the base of induction is trivial, like for a one vertex graph, the statement is trivial. So then the step of induction, basically we take any vertex in the graph V and we remove it from the graph, and for the rest of the graph is G minus V. So without this one vertex, we applied the inductive hypothesis, and we can apply it because the maximum degree in this graph would be less or equal. So the maximum degree of this graph G minus V is less or equal than the maximum degree in G. So then we apply it, we get a coloring into delta plus 1 colors. So by inductive hypothesis, this graph G minus V is colorable into delta plus 1 colors, and then we need to extend this coloring to the remaining vertex V. So the vertex V, it has at most delta adjacent vertices, right? Because delta is the maximum degree among all vertices. So the degree of V, in particular, the degree of V is less or equal than delta. The degree of V is less or equal than delta. And so now, so let's write delta. So let's denote delta of G. We'll just write delta, so that like for convenience. So now we have less or equal than delta vertices adjacent to V, and we have delta plus 1 colors, right? So because like we need to color the graph into delta plus 1 colors, because the chromatic number is less or equal than delta plus 1. It exactly means that the graph G is colorable into this number of colors colorable properly. So we have delta plus 1 colors. So therefore there is at least one vertex, there is at least one color that is not used on this vertices adjacent to V. So there exists at least one color. Let's write it, at least one free color. For the vertex V, because again we have delta plus 1 colors and delta of them are taken. So we have at most delta vertices adjacent to V, and each of them is colored into some color. Like there could be some of them could be colored into the same colors, but in the worst case they're all colored into different colors. But regardless, the number of colors taken by these vertices is at most delta. So from this we can write that at most delta colors are taken Okay, let's write it more carefully. Most delta colors are taken by these vertices. So there is at least, and in total we have delta plus 1 colors. So delta, at most delta colors are taken, so and the total delta plus 1 color, so at least one color is free. So it's not used by these vertices. Therefore, we can use it for the vertex V, because this would not violate the condition of proper coloring, because all vertices that are adjacent to V would be colored into different colors. So that and then we color V in this color. And this concludes the proof. So now basically the Brooks theorem is an improvement of this upper bound, in that, like, we want to drop this plus 1, because in the Brooks theorem it says that Q of G is less or equal than delta. So now we observe that we cannot drop plus 1 for all graphs, because there are two graphs or two families of graphs for which this inequality becomes is attained, for which this inequality becomes inequality. And so these two families of graphs is the complete graph on n vertices, on any number of vertices. So this is a complete graph and an odd cycle. An odd cycle. And you notice that for, so let's calculate for both of these families of graphs. So a complete graph is a graph where all vertices are pairwise connected. All pairs of vertices are connected to each other. So this is K5. So notice that since all pairs are connected by an edge, we need different colors for any pairs of vertices. So basically we need all different colors for all vertices, because like if any two pairs would have the same color, then we would have a violation of the condition, because any two pairs are connected by an edge. So the chromatic number of Kn is equal to n. We need n colors. Each vertex gets its own color. And the maximum degree of Kn is equal to n minus 1, because every edge, every vertex is adjacent to all other vertices, and the number of other vertices is n minus 1. We have n in total. This one vertex that we are currently considered, like, it's not adjacent to itself, of course, and to all other n minus 1 vertices it is adjacent. So we have this, and so we see that for Kn we have he of Kn is exactly equal to delta of Kn plus 1. So this inequality is exactly is attained. We have an equality here. And for an odd cycle, so we have for an odd cycle, so we have, so this is C5, right? So it can be colored into 3 colors. We simply alternate colors until the last vertex. When we go to the last vertex, we see that we cannot color it into color 1 because it would be adjacent to this, and we color it into color 2 because it is adjacent to this. So for the last vertex we need to use the third color, but we can always color into 3 colors. We alternate the colors until the last vertex, and the last vertex we color into the third color. So this shows for now that the chromatic number is less or equal than 3 because it is 3 colorable. Now, why it is not 2 colorable? Well, the even cycles, they are actually 2 colorable. We can just alternate the colors and that's it. So, but odd cycles, they are not 2 colorable because there is a theorem that like a criterion when a graph is bipartite, and bipartite graphs are exactly the 2 colorable graphs. And the theorem says that a graph is bipartite if and only if it doesn't contain odd cycles. And so an odd cycle itself is an odd cycle, so of course it contains an odd cycle. So therefore it is not 2 colorable by this theorem. And therefore, not 2 colorable, it means that he is greater or equal than 3. So because it's less or equal than 3 and greater or equal than 3, then it is exactly equal to 3. So the chromatic number of odd cycles is exactly equal to 3. And the maximum degree of an odd cycle, of course, is equal to 2. So because every vertex is adjacent to 2 vertices, exactly 2 vertices. So it's a 2 regular graph. So the maximum degree is also 2. So here I see that also he of CO2n plus 1 is exactly equal to delta of Cn plus 1 plus 1. So because 2 plus 1 is equal to 3, right? So yeah, so again we have the equality here for this inequality. So, and basically the Brooks theorem says that these are the only two exceptions. So for all other graphs, yeah, there is an additional condition that connected. So the Brooks theorem considers only connected graphs. It's a very important additional condition. So for all other connected graphs, the upper bound can be improved by 1. So let's write this. So Brooks theorem. So for every graph that is connected, G is connected. Yeah, so it's a very important condition actually, because like sometimes when you read the theorem, you can miss it because you read about the these two families of exceptions, and you completely miss the condition that it is connected. But it is an important condition. It will be used in the proof, because the original theorem like this. Yeah, because the original theorem, this original upper bound, it holds for any graph connected or disconnected. We don't assume the connectedness here, but in this Brooks theorem, it holds only for a connected graph. Okay, so for any graph G that is connected and G is not equal to the complete graph Kn and G is not equal to an odd cycle, then it follows that the upper bound, the chromatic number of G is less or equal than the maximum degree of G. Yeah, so without plus 1. So basically the general upper bound is improved by 1. So yeah, so let's prove this. And so the general idea of the proof is going to be the same. So we are going to use induction on the number of vertices, but it's much more difficult to prove than the original upper bound. So first we are going to before proceeding to induction, first we are going to separately consider the cases of small maximum degree. So when the maximum degree of the graph G is equal to 0, when it's equal to 1, and when it's equal to 2. So these 3 cases we are going to consider separately. So first, when the maximum degree is 0, so this means actually that there are no edges in the graph. So it's the graph consists of isolated vertices, but because it is connected, so again we assume that the graph is connected. So because it is connected, then it's only a single vertex. We can't have more than one vertex. So it's only so this is from the connectedness of the graph. So it's only a single vertex, and for a single vertex, like of course we have the single vertex is actually a single vertex which is also K1, right? So K1 and Kn is an exception. So because of this condition, we this case is we are done for this case. So then the case of maximum degree equal to 1. So this means that the degrees of all vertices are either 0 or 1. This means that all the vertices are divided into these pairs of vertices. So we have edges that connect some vertices, and we possibly have some isolated edges as well. So this is like all graphs that have maximum degree 1. So again, because of the connectedness of the graph, we either have, so we cannot have these isolated edges at all, isolated vertices at all, and the edges also, we can have at most one edge, because if we have at least 2, then this graph is not connected. So because of the connectedness, so we have a single edge basically. The graph consists of a single edge. So 2 vertices, 1 edge, but this is equal to K2. So this graph is a complete graph on 2 vertices. And so again, we are done for this case, because this is a complete graph is an exception from the theorem. For a complete graph, we don't need to prove our upper bound. So now the case when the maximum degree is equal to 2. So here we have so any vertex is adjacent to at most 2 vertices. So then basically when we go, so we start from some vertex, we move to the next vertex, then so we came here by one edge, there is at most one other edge, so either we stop or there is another edge. So sooner or later we will come to the vertex that we already visited, right? It cannot be some intermediate vertex, because then we will have this vertex would be adjacent to 3 vertices. So then the only vertex where we the only repeated vertex in this process would be the original vertex. So either we have this cycle, or we will stop at some point where there is no more edges out of this vertex. So basically we have a collection of so each connected component is either a cycle or a path. But because it is a connected graph, so we have only one connected component. So we have either a cycle on n vertices or a path. I'm not sure how a path is denoted, but let's denote it as Pn. So this is a Cn, this is Pn. And n might be different for, like here for different connected components, n might be different. So let's write n prime here. So Cn or Pn, and for both of them, so if it's a path, so let's consider these two cases now separately. So for a path on n vertices, and Cn is a cycle. So for a path on n vertices, we have the chromatic number is equal to 2, because it can be colored into 2 colors by alternating colors, and of course it's not one colorable if n is at least 1, f is at least 2. And if n is 2, then we have k2. So n is at least so the chromatic number of Pn is equal to 2, and the maximum degree of Pn is equal to 2. So the inequality clearly holds. So this inequality, he less or equal than delta, is like it holds here. And for a cycle, so again, if it's an odd cycle, then we don't need to prove anything, because the odd cycle is an exception. And if it's a so here, like here, so this is for n greater or equal than 3, and for n, so because if n is equal to 2, then we have a single edge, then delta would be 1, but then single edge is a k2, so this is an exception. So for P2 is the same as K2. So this is an exception, and for n greater than 3 we have this. So now for cycles, so an odd cycle is an exception from the theorem, we don't need to prove anything. So for an even cycle we have for an even cycle, so it is two colorable by alternating the colors. At the last vertex we wouldn't have an issue here with the first vertex, because it's an even cycle, and so the chi of C2n is equal to 2, and the delta of C2n is equal to is equal to 2. So again, the inequality holds. Yeah, so this so basically this concludes the proof for these cases of small delta. So for the rest of the proof we will assume that, so we assume that the maximum degree is greater or equal than 3, and we will use it actually at the variant of the theorem. So, and now we can proceed with induction. Okay, so now we use the induction. Induction on the number of vertices in the graph. So we so when the basically the base of induction, when there is only one vertex in the graph, then the theorem trivially holds. We have basically G is equal to K1, and the theorem trivially holds. So then the inductive step, so we assume that, suppose that the statement holds for the number of vertices strictly less than n, and consider a graph with exactly n vertices. So the scheme of the proof kind of in general is the same. So we pick a vertex, we remove this vertex v, and apply the inductive hypothesis to the rest of the graph. But we need to be careful now. So first, the case when so if there is a vertex so if there exists a vertex v with the degree strictly less than delta, so less or equal than delta. By delta, like let's write somewhere separately here that we are going to denote delta. Instead of delta of g, we are going to write delta. Delta is going to be just delta of g, just for brevity. So when the degree is delta minus 1, so if there is a vertex then with the degree strictly less than delta, so at most delta minus 1, then we pick this vertex v, and here is the rest of the graph, g minus v. So now this is only one case. Later we will consider the case when there is no such vertex. So Now we need to be careful because we cannot really apply the statement to this graph G minus V because it might be disconnected. So because unlike the previous theorem with the trivial upper bound of +1, so unlike this theorem when we have +1 which holds for any graph connected or disconnected, here G must be connected. So when we use the induction, we cannot directly apply the inductive hypothesis to this graph G minus V because we don't know if it's connected or not. So what we can do is only to apply it to every connected component in the graph. So let's denote all connected components in the graph as H1, H1, H2, and so on, HK. So these are the connected components of this graph. So H1 and so on, HK are connected components of G minus V. So then we notice that, and we apply the theorem to the inductive hypothesis to all of them. So we apply the inductive hypothesis to this H1 and so on HK. So notice that the maximum degree of HI for any I is less or equal than delta, less or equal than the maximum degree of the original graph. Now but it's actually so less or equal than delta. So now we also don't know if these connected components are complete. So some of them might be complete graphs or odd cycles. So we don't know if they're complete graphs or not. So we need to consider both cases. So if HI is not a complete graph and not an odd cycle, so if HI is not Kn and HI is not C2n plus 1, then by inductive hypothesis the He of HI is less or equal than delta of HI, which is less or equal than delta of G of the original graph. So now if HI is equal to Kn or HI is equal to C2n plus 1, then He of HI is exactly equal to delta of hi plus 1, but in this case, so in this case of this hi, so let's say that sum of this hi is equal to kn or c2n plus 1. So in this case, for the whole graph to be connected, because remember that the whole graph G must be connected, the original graph G. So for this graph, for the whole graph to be connected, the only way like it must be connected to the vertex V. So the vertex V must be connected by some path to this component hi, right? So this means, but it cannot. So this is a component of G minus Y. So it doesn't, like, it's not connected to any other vertices in G minus V. So the only way for it to be connected to V is to have an edge to V. So there is an edge directly from V to some vertex in this graph, in this hi. That's the only possibility. And this for any component, actually. Even if G minus Y is connected, so even if it's the only connected component in G minus V, it still must be connected to V somehow. And the only way for it to be connected to V, because the whole graph is connected, the only way for it to be connected to V is to have an edge between V and some vertex in this graph. So because of that, the maximum degree, because there is an extra edge from this edge from this hi to V, so delta, so it follows that delta of hi is actually less than equal than delta plus delta minus 1. Because in this okay, let's prove this more carefully. So if this is kn, so if this is kn, so this hi is kn, so there is so every vertex, so then delta of kn is equal to n minus 1, right? So n minus 1, but there is a special vertex, at least one, in this graph that is connected to V. So this vertex has degree in the original graph. So let's denote this vertex by U. So the degree of this vertex in the original graph G of this vertex U is equal to n. So from this it follows that the delta maximum degree in the whole graph G is greater or equal than n, and n is, from this, n is equal to delta of kn plus 1. So and from this we conclude that delta of, well, basically this inequality delta, but we like delta of hi plus 1 is less than equal than delta. And similarly for similarly for the case of C2n plus 1. Again, in this case, delta of C2n plus 1 is equal to 2. Then vertex V must be connected to some vertex in this cycle. So this vertex denoted by U. This vertex U has degree 3, at least 3. Yeah, so it's not exactly n. It's not exactly n. It might be even more, but it's at least n. It's at least n. Oh no, I think it's exactly n. Yeah, it's exactly n because there is nothing else to be connected to. So it's because it's a connected component in G minus V, and the only vertex to which it can become connected anymore is only the vertex V. So it's exactly n. Yeah. So so here delta is equal to 2, and so the degree in the graph G of this vertex U now is 3, because this vertex is not connected to anything else, only to V and to inside this connected component in G minus U. So its degree is exactly equal to 3, and from this it follows that delta is greater or equal than 3, which is equal to delta of C2n plus 1 plus 1. So, and in this case as well, we have that delta of hi plus 1 is less or equal than delta. So in both cases, when like in these two cases, when hi is either a complete graph or an odd cycle, we have this inequality. Delta of hi is less or equal than delta minus 1, or delta of hi plus 1 is less or equal than delta, in this form, as I wrote it here. So by inductive hypothesis we have this. Well, this is not by inductive hypothesis, but from the from what I proved previously, that for a complete graph and not cycle we have the exact equality here, and this by this inequality now this is less than equal than delta. So in both cases now, this and this, in both cases we have that he of hi. So in both cases we have he of hi is less or equal than delta. Yeah. So we need to consider the cases of a node cycle and the complete graph separately, but in these special cases we have get an extra +1 here because of the connectedness of the original graph. So that's where we use the connectedness to get an extra 1. So in both cases this is less than delta. And this is actually holds regardless of if there is a vertex v, regardless if the degree of v is less or equal delta minus 1 or not. We didn't use this condition anywhere yet. So so we will reuse this result for a later case when the degree is not when this does not hold. So now basically we proved that so because this holds for any connected component hi, so from this it follows that the he of the whole graph g minus v is less than equal than delta, because the colorings of the connected components, we merge them together into coloring of the whole of the whole g minus v graph, right? So so if it holds for all connected components, then it holds for the whole graph g minus v. So basically we proved now that if we remove any vertex from the graph, then he of g minus v is less or equal than delta. That's what we proved. So again, we cannot obtain this directly from the inductive hypothesis for g minus v, because it might not be connected. So we need to consider all connected components and all this argument. We need to like the special cases for complete graph and odd cycle, and so like all this argument. But in total, we get the result as if we apply the inductive hypothesis to the whole graph. But we don't. It's a more complicated argument. So now, so basically from here, like we didn't use this condition, so let's even remove it from here. So this applies to any vertex v, regardless of its degree. So now if there is a vertex v, so if there exists a vertex v with degree less or equal than delta minus 1, then we pick this vertex v, we get this result that it's less than delta. So now we have now in this case we have less or equal than delta minus 1 neighbors of v in this graph g minus v. So it is colorable into delta colors by this, and we have at most delta minus 1 neighbors of v in this graph. So there is a free color for v. So there is a free color for v, because we have delta colors and delta minus 1 neighbors of v. So at most delta minus 1 colors are prohibited, so there is at least one free color, and we color into this free color, and so this way we extend the coloring of G minus V to the whole G. So we color V and we extend the coloring to the whole G, and so it's also delta colorable. And this basically concludes the proof in this case. So if there is a vertex with the degree, basically it's the same argument as in the original upper bound. Like if the degree is 1 less than delta, then we use the same argument, and since in the upper bound there is the upper bound is less by 1, so it's natural that we get the same result. So basically this case is easy. The proof is similar to the original upper bound, and the only remaining case, is when all vertices in the graph have degree exactly delta. So it's the maximum degree, and it's also the degree of all vertices, and the only degree. So basically G is delta regular. So when all vertices in the graph have the same degree, the graph is called regular. And if the degree is delta, it's called delta regular. So that's the only remaining case. So that's what we consider. So now we pick any vertex V. We pick any vertex V, and we use the same argument, the same inductive argument. So we remove this vertex V, and we consider G minus V. So now suppose that we cannot color G. So G minus V is, so G minus V is delta colorable by this, what we proved. So G minus V is delta colorable. Suppose this is by contradiction. So suppose that G is not delta colorable. Like if it is delta colorable, that's what we need to prove, basically, that it is delta colorable. So suppose it is not delta colorable. It is not. It is not delta colorable, and the only possibility when this can happen is when so it has delta neighbors in this J minus V, and all of them are they have exactly delta colors. So all neighbors. So if it's not delta colorable, it implies that all neighbors of V, or all adjacent vertices of V, have all delta neighbors, because the degree is delta. The degree of all vertices is delta. All delta neighbors of V have all delta colors. Right? So if it has all delta colors, so we denote the colors by 1 So colors denoted as a set 1, 2, and so on delta, just for convenience. So these are the colors, and so we denote now the vertices of this neighborhood of V, so the adjacent vertices to V, denote them by V1, V2, and so on, V delta, and VI has color, like enumerate them in such a manner that VI has color I. So since there are delta vertices and delta colors, so we can enumerate them in such a way that so V1 has color 1, V2 has color 2, and so on. V delta has color delta. So Vi has color I for all I. So now we have like denote several more things. So we denote by HIG, denote the subgraph is the subgraph of G minus V, so of this graph. Spanned by vertices of colors E and G. So we take only the vertices of colors E and G, I and G, and this is the subgraph. And so now, and it depends on the coloring. So notice that like we fixed the coloring. So we fixed the coloring here. Fix the coloring. Fix the coloring in delta colors. So we proved that He of G is less or equal than delta, and we fix the coloring in delta colors. So it's delta colorable, fix the coloring in delta colors. So now these definitions of VI, so V1 and so V delta, this it depends on the coloring, and HIG is also depends on the coloring. So now we will prove several claims. So claim 1. So claim 1 is that well, so let's yeah, so we will need this yeah, so all delta neighbors of V have all delta colors. We'll call this as a claim 1. So this is for any coloring, right? So all neighbors of V have all delta colors. So we'll call this as claim 1. Claim 1. So now claim 2. Claim 2 is for any I and G not equal to each other, so E is not equal to G, the vertices VI and Vj lie in a common component. Yeah, we need another notation. So here, so before writing the claim, so let's denote one more thing. So denote Cij is the no, we'll denote it later. Okay. Yeah, first we need the claim. So okay, so for all ij, I is not equal to j, the vertices vi and vj belong to the same connected component of hij. So first, they both belong to hij, obviously, because hij is the subgraph of the vertices of colors I and j. So vi is color I, vj has color j, so they both belong to this subgraph. And now this claim says that they belong to the same connected component of the subgraph. So basically, vi and vj and vj, so they are connected by some path. Using only colors I and j. So some path in this subgraph. So it means that they are connected by a path using only colors I and j. All vertices on the path have only colors I and j. So that's what this claim says. And we will denote, so like after we prove this claim, so we will denote this connected component. So denote this connected component by Cij. Yeah, so we cannot define it like initially I wanted to define it before, but we cannot define it until we establish that they are in the same connected component. So okay, so now let's prove it. So suppose by contradiction that they lie in different connected components. So there is no such path between Vi and Vj. There is no such path between Vi and Vj using only the colors I and j. So then, so basically they lie in two different connected components. to different connected components. And so let's switch the colors. So in one of them, let's pick one of them, let's say this one, and switch the colors I and j in this connected component. So by switching the colors I and j between each other, we don't violate anything. So so inside this connected component, like, because if the vertices this connected component is basically a bipartite graph, right? So we can draw it like this. I and j. So by switching the colors I and j between each other, like it still would be colorable it still would be a proper coloring, and since it's a connected component, we don't violate any edges that come out of this. So any edge that come out of this, so if this colored in I or j, then at the other end of this edge is not I and not j. So by switching colors I and j inside this connected component, this would be still a proper coloring. Switch the colors of I and j, this would still be a proper coloring of the graph G minus V, right? But now after this switching of the colors, Vi now, the vertex Vi, this vertex Vi would be colored J. So after so it's still a proper coloring of G minus Y, but Vi is colored J. Colored is color J, and Vj is still colored. Vj is still colored with color J, right? So Vi and Vj now colored the same, in the same color J. So we return here to this original image. So now this delta vertices, two of them now colored the same. So it's still a proper coloring, but two of these vertices are colored the same. So this creates a free color for V, and this is actually a contradiction to claim 1. Because in claim 1, in any coloring, so because claim 1 holds for any coloring, right? So all delta neighbors of V have all delta colors. But here after recoloring, we obtain a proper coloring where two of them, Vi and Vg, now colored in the same color. So a contradiction to claim 1. Or another way would be just this creates a free color for vertex V, and we are done with the induction, with the inductive step. So claim 2 now is proven. So this concludes the proof of claim 2. So the contradiction appeared because we assumed that Vi and Vg lie in different connected components. So then one of the connected components, in one of them we can switch colors, Vi and Vg. If they're in the same connected component, then switching colors I and G doesn't then Vi would be colored J and Vj would be colored I. and we still would have delta colors among the adjacent vertices of V. So this wouldn't create this contradiction. So the only source of the contradiction is that Vi and Vg belong to different connected components. So therefore they must belong to the same connected component. So to the same connected component of this graph, and we denote this component by Cig. Okay, so now we define this Cig, and so now claim 3. So claim 3, or we could call them lemma, I guess, instead of claim, but it doesn't matter. So claim 3 is that Cig is not just a connected component, but it's a path. It's a path. It's a path between Vi and Vj. Okay, so if so since Vi and Vj lie in the same, belong to the same connected component, so there is some path between Vi and Vj. There is some path in this connected component between Vi and Vj, and of course the colors must alternate on this path. So this is color E, this color I, J, I, J, I, J, I, J. So there is some path. Suppose that it's not the whole connected component. So there is something else in this connected component. Yeah, so if there is something else in this connected component, then we consider first, so we consider basically two cases. When this something else is inside the path, so when some internal vertex on this path is adjacent to some other vertex here, and when the boundary vertex, so either Vi or Vj, is connected to some other vertex. So let's first consider the case of this Vi. So let's say that Vi is also, so there is also a vertex, of course it has color J, that is adjacent to Vi in this connected component Cij. So so the degree, so notice that Vi and Vj are the vertices that are connected to V. So there is somewhere here this vertex V that is external to the graph G minus V. right? So this is the graph G minus V. So Vi and Vj are connected to V, and so because the degree, so the degree in the original graph is delta, so the degree of the vertex Vi in the graph G, in the whole graph G, is less or equal than delta, and to one vertex it is connected outside of this G minus V. So in the graph, so the degree of this vertex in the graph G minus V, of this Vi, is 1 less, is delta minus 1, is less or equal than delta minus 1, because one edge goes outside of this graph. So yeah, so now this vertex Vi, so it has degree, so in this graph G minus V, it has degree at most delta minus 1, and it has two adjacent vertices of the same color, right? So it has, so this Vi now, so what are basically the options to color Vi? So we have, so among delta minus 1 of its neighbors, two of them have the same color J. So in total, at most, so we have, so three colors, so basically three colors for Vi. What are the three colors for Vi? So we have, so it has less or equal than delta minus 1 neighbors, and two of them have the same color. So the three colors for Vi, we have, so basically delta, so we have delta minus, so the three colors for Vi, so this is what we're calculating, delta minus at most delta minus 1 neighbors, plus two of them have the same color, so delta minus 1 minus 1. So among these delta minus 1 neighbors, there is at most delta minus 2 colors. So this delta minus 1 neighbors, let's write this, they take less or equal than delta minus 2 colors, because two of them have the same color, J. So delta, so the three colors would be now delta minus delta minus 2. So this is equal to 2. So we have two free colors for Vi. So one of them is I, of course, which is, it is already colored in I. But since there are two free colors, there is at least one other color. So there is at least one other free color for Vi except I. So there exists at least one other color one other than I, and one color other than I, at least one color other than I, that we can color Vi. So let's switch this, so recolor, now recolor. So therefore recolor Vi into this color. So recolor, and then we would get so Vi would be the same color as one of the other, Vk, let's say. So this would be a contradiction to claim 1. Yeah, because claim 1 says that all neighbor in any delta coloring of this graph G minus V, so all neighbors of V have all delta colors. But if we recolor one of them, Vi, to another color, keeping the coloring proper, so then these vertices Vi and so on V delta would have one less color. So this would be a contradiction to claim 1. So then the other case is when, so this proves the case when one of the boundary vertices Vi or Vj is adjacent to some other vertex in this connected component except on the path. So, and another case is when some intermediate vertex, so let's say this vertex colored I, so this is again connected to another vertex of color J in the same connected component, not on the path. So we have a path between Vi and Vj, and some intermediate vertex is connected to some other vertex. So in this case, again, what we have is basically this vertex of color I has 3 neighbors of the same color. So basically the same argument, except the difference is that this vertex is not connected to V. So we don't have this degree less than delta minus 1. It's just less than delta would be. But here we have 3 vertices of the same color J instead of 2. So the same argument. So similar argument. Except now so let's denote this vertex X. Let's say this vertex X that is adjacent to another vertex of color J. So the degree of this vertex X in the graph G minus V is less than or equal than delta, but it is connected to, so this vertex X, it is connected to 3 vertices, so it itself has color I, it is connected to colors to 3 vertices of color j. And like I, it's just without loss of generality. If it's color j, then these 3 would be colored I. And the same for, like here we considered the case of vi, but the same is considered the case of vj. So if there is if vj is adjacent to another vertex here. Okay, so the degree is less than delta, and 3 of these adjacent vertices have the same color. So 3 colors for x. So 3 colors for the vertex x. So there are delta in total. Delta colors in total, and it has delta neighbors, but 3 of these vertices have the same color. So basically, we need to subtract 2 from delta. So this is again equal to so again delta, just to explain a little bit more. So delta minus 2, this is the number of colors that the neighbors of x take. So this is the number of colors that neighbors, at most the number of colors, so less or equal than the number of colors, neighbors of x take. Well, I guess the number of colors is less than equal than delta minus 2. The most number of colors, the maximum number of colors that the neighbors of x take. There are at most delta neighbors, but 3 of them have the same color, so we need to subtract 2. That's why delta minus 2. So we have 2 free colors for this vertex x, so one of them is I, and there is at least one other one. So we can recolor. So similarly to the previous case, we can recolor x. Okay, so let's continue the proof. So here we don't yet have a contradiction. So in addition to what we already did, we need to make an additional adjustment in the proof. So here we take not just any vertex x with such a property that that is connected with like to some other vertex of color I or j on the path, but first such vertex on this path. So x. So x we take it's the first such vertex on the path. So basically we start from this vertex vi and we move along this path. So we already proved that vi itself is not connected to any other vertices of color I and j. So we move along this path, and we take, so we move to the next vertex. We check if is this vertex connected to any other vertices except those on the path of color I and j. If not, then we move to the next one, and so on. And the first time that we arrive to a vertex that is connected to some other vertex of color I or j that is not on the path, so like this, then we take this we denote this vertex by x, and we take this vertex and we do what we previously did. So it's not an arbitrary vertex on the path, but the first on the path when moving from vi to vj. So in this way, so if it is the first vertex, then by recoloring, so when we recolor this vertex x, then we disconnect. So then this disconnects vi from vj by the vertices of color I and j. So basically in in the subgraph hij. Because if it was the first such vertex, then the vertex I is no longer connected. So the only vertices of color I and j it is connected to is this beginning of the path, and is not then vi is not connected. By path, connected in the sense of belonging to the same connected component. Not adjacent, but connected by a path. So it's only connected to the beginning of this path. It's not connected to anything else when we recolor x. So because if x was an arbitrary vertex such that it is connected to some other vertex of color j, then there could be possibly another path like somewhere here around this vertex x that connecting the beginning of the path to the end of the path. But because we took the first such vertex x, there could not be such a path around, because if it was, then we would take this vertex that is branching from this path. We would take this vertex first instead of x, because this vertex would be connected to another vertex of color I or j on this path, not on this path. So so all of this to say that by recoloring the vertex x, we disconnect vi from vj. So this disconnects vi from vj, and in this new coloring, so this contradicts. So in this a contradiction to claim 2. Because in this new coloring, after the recoloring of the vertex x, because the claims 1 and 2, like all the claims, they're applied to any coloring of the vertices. So after this recoloring, we get that vi and vj are not connected by the colors I and j, and so therefore the claim 2, which claimed that vi and vj belong to the same connected component, this claim would be violated. So this concludes the proof of claim 3. Now there is a a couple more claims. So claim 4. So claim 4 says that, as a reminder, claim 3 said that Cij is a path. So Vi and Vj don't just belong to the same connected component, but the whole connected component consists just of a single path between Ci and Cj. There cannot be anything else. And now claim 4 says that this path could not intersect with each other except at the ends of the path. So for any I, j, k, the path Cij, well, of course, like I not equal to j and j not equal to k, and k not equal to I. So all these indices are different. So Ci and Cj and Cjk intersect only at Cjk, only at Vj. So they cannot intersect at any other internal vertices in the path. So basically, like, we have vertex Vi, vertex Vj, and vertex Vk, and so the connected components Cij is a path, Cij, Vjk is a path, Cjk, and the only vertex where they intersect, these two paths between each other, is the vertex Vj. So they cannot intersect in any other vertex. So there cannot be a situation like this. Basically, when there is another vertex, so from Vj there is a path, it goes like this. There is a common vertex other than Vj on these two paths. So let's prove this. So suppose by contradiction, suppose that there is such a vertex, and like we will use a similar argument that we already used multiple times. So this vertex, of course, must have color J, right? So yeah, so let's see this more in detail. So this vertex must have color J, because the path Cij has only colors I and J, and the path Cjk has only colors J and K. So the only common color is J. So there is no other options for this. So let's look at, but on the path, the vertices alternate colors. So we take the previous vertex here and the next vertex here on the path, right? So this must have color. Okay, so let's draw this on another picture. So basically we have this and this. So this is Cjk and this is Cij, right? So this is the vertex U and it has color J. It must have color J. So Vj is somewhere here. Vi is somewhere here. And Vk is somewhere here. So we consider the previous and the next vertices on the path, on both paths. So we have these 4 vertices, right? So the vertices alternate colors on the path, because like it's a proper coloring and the path has only colors I and J. So if this is color J, so the previous color must be I and the next color must be I. So and similarly on this path as well. So the previous vertex has color K and the next vertex has color K. So basically we have this combination when the vertex of color J has two vertices, is adjacent to two vertices of color I and to two vertices of color K. So, but this again, like this creates an additional free color for the vertex U, because if we count the free colors, so like every time we have the same color, a vertex is adjacent to two vertices of the same color, it creates an additional free color for the vertex, right? So, so free colors for the vertex U. So we counted. So we have delta colors in total, and we subtract the number of colors that are already taken in the adjacent vertices, the maximum number of colors that could be taken. So for like vertices that is, so other vertices that are not drawn in the picture that it is adjacent to, we don't know their colors, but we know that in total delta is the maximum degree in the whole graph G. So there are in total at most delta adjacent vertices of this vertex U, and 4 of them take 2 colors. So these 4 vertices take colors I and K. So 4 of these vertices take 2 colors, and the rest, delta minus 4 vertices, take at most delta minus 4. So at most we have delta minus 2 colors that are already taken, right? Yeah. So delta minus 2 colors that are already taken. So we have two free colors. So one of them is J. So J is a free color because it's already colored J. So therefore there is another free color. So therefore there exists at least one other free color for U, for the vertex U, and we recolor the vertex U, and what happens is that so this disconnects yeah, so this disconnects well both of these paths. So Vi from Vj, Vi from Vj and Vj from Vk. So and this is a contradiction to claim 2 again. This is a contradiction to claim 2, so this concludes the proof of claim 4. So claim 4 says again claim 4 says that they're not just any path, but this path don't intersect with each other except at the ending vertices, at the vertices vi, vj, like v1 and so on, v delta basically. So they don't intersect at internal vertices. So okay, so now we have claim 5. Now we have claim 5. And claim 5 says that this is that they are not just not intersecting at any other vertices, but claim 5 says that Cij, so for any I and j, Cij is a simple edge. Is a single edge. This path consists of a single edge. Is a single edge, vi, vj. So this whole path is just of length 1. Yeah, and this would be like if you prove this, this would be almost the proof of the whole theorem. The theorem would easily follow from this. So, okay, so let's prove this. Suppose, on the contrary, that this path from so suppose that so by contradiction, right? So we prove by contradiction. So suppose that there exists such I and j that Cj is not an edge, is not a single edge, So therefore it has length, the length of Cij is at least 2 edges on this path. So so we have this vi, vj, and there is at least on this path there is at least another vertex, so denoted by u. There is at least another vertex, and then there is a path that eventually come to vj. But there is at least so u is an internal vertex on this path. So then so the vertex vi of course has color I, vertex vj has color j, and this vertex u has also color j, because the vertices on the path have alternating colors. So yeah, so now we will use that delta is at least 3. So you remember that at the beginning of the proof we separately considered the cases of small delta. So when delta is equal to 1 or 0 or 2. So we separately considered these cases, and so for the remaining of the proof we assumed that delta is greater or equal than 3. So here we will use that delta is at least 3, and we will use it to conclude that there exists one other vertex vk. So there exists at least another other vertex vk. So there exists, so because delta is at least 3, so we have in total like we have the vertices v1 and so on v delta. So we have delta of them, right? So because delta is at least 3, we have 2 of them. We took already 2 of them, vi and vj. So there exists at least one other. So there exists k such that k is not equal to I and k not equal to j, such that well k belonging to the set from 1 to delta. So that there exists this vertex vk. Okay, so or we can write like basically there exists, instead of exist k, we can write exist vk, such that k is not equal to I and not k equal to j. So and now we consider the yeah, so in the path, so now there is a path from I to k. So this is the path c I k. So we consider this path c I k. So and this is the path, of course, c I j. So so in this path CIK, so in this path CIK, we will switch the colors I and k. We can always do this because all the colors I and k, they are on this, the vertices of these colors, they are on this path, because we proved that they are on this path. This is the path. The whole component, the whole connected component is this path, and if we switch the colors, so the colors alternate on this path, and if we switch the colors, the coloring still would be proper. So it still would be a proper coloring when we switch the colors. So and denote this new coloring by, so denote the original coloring by C, and this new coloring after the switching the colors denoted by C prime. And so this new color in C prime, it also, like, since it's also a proper coloring, it also has these vertices V, like Vi, like V1 and so V delta. It has this path Cij and so on. So we denote all these sets because all of them are defined. Like, recall that Vi is defined based on the coloring, so for a fixed coloring. So for a new coloring, we denote all these vertices and path with the prime. So we have now the vertices v1 prime and so on. For the new coloring C prime, v delta prime, we have this path C ij prime for any ij is already taken, so ij are here fixed letters, so like cxy, let's say cxy prime. So notice that now vi, so v vk prime is actually vi. So this is the same vertex, because in the old coloring it is colored I, in the new coloring it is colored k, because we switched the colors, interchanged the colors I and k. So, and vice versa. So vi prime, this is the vertex vk. So so now consider this vertex u. So the vertex u has color j, and it is adjacent to the in the new coloring. So it still has color j, and it is adjacent to the vertex of color k. So u now must belong in the new coloring. It must belong to the connected component c cjk, right? Because it is itself has color j, and it is connected to it is connected to vi, which is vk prime. So in prime. So in this prime coloring, C prime, it must belong to this connected component cjk prime. Okay, but notice that the remaining of this path, so the remaining of this path retained its like all its colors. So there is at least one vertex, one more vertex here. So this is Cij. So there is at least one more vertex here, because both u and vj has the same color j. So there must be at least another vertex here. The next after u has color I, because u cannot be directly connected to vj, they have the same color. So there is at least another vertex I. So this remaining of this path, it retained its color because it's not intersecting with Cik. So from the previous claim 4, Cij and Cik do not intersect with each other at internal vertices. So this part of the path Cik from U to Vj, Cij from U to Vj, it retained its color. So in particular, this is vertex of color I. So this means that this part of the path must belong to C J. So Cij prime. So in particular U, which is part of this remaining of the path. So the vertex U in particularly must belong to this Cij prime because it is connected by a path to Vj of so it is connected by a path of colors J and I to Vj. So therefore it belongs to the, by definition, it belongs to this connected component Cij prime in the new coloring. Right? So now from this we get that U belongs to both of them. So Cij prime and Cjk prime. So Cij prime and Cjk prime, and also of course U is not equal to Vj. U is not equal to Vj because U, like by our assumption, U was an internal vertex on this path from Vi to Vj, so it's not Vj. So from this three, so U is an internal vertex. U is an internal intersection, internal intersection vertex and the vertex in the intersection Cjk prime and Cij prime. So, and this is a contradiction. A contradiction to claim 4, to the previous claim. This concludes the proof of this claim. Because again, claim 4, it applies not only to the coloring C, but to the coloring C prime as well. So it applies to any coloring. So this proves claim 5. So this is almost it for the theorem. So claim 5 says that all this path Cij, they consist of a single edge. So now let's examine what we actually have. So we have this, return to the original theorem. Right, so we have this vertex V, and we have this remaining graph G minus V. and V is connected to delta vertices, which are exactly the vertices that we denoted V1, V2, and so on, V delta. And under the assumption, so recall that we proved these claims, claim 1 through claim 5, we proved them under the assumption that V cannot be colored. So under the assumption that inductive step does not work. So we cannot extend the coloring from G minus V to the vertex V. So, and under this assumption, we proved all these claims that ultimately claim 5 says that the coloring basically consists, so like the colors 1 and 2, for example, between so V1 is colored into color 1, V2 is colored into color 2, and the whole connected component of colors 1 and 2 consists of a single edge. So there is nothing else of colors 1 and 2. And so and any two vertices here are connected to each other. So in particular, the graph on the vertices, so if we take the subgraph on these vertices V1, V delta, this subgraph, it is a complete, so the subgraph on this vertices V1, V delta, this is a complete graph on delta vertices. So any two vertices in this list are adjacent to each other. This follows from claim 5. So now let's consider now the degree of each of these vertex. So let's say vertex Vi. So it is. So there are these vertices V1 and so on, V delta without Vi, right? Without Vi itself. So there are delta minus 1 such vertices, right? So it is connected to delta minus 1 of these vertices. Plus it is connected to to V. It is adjacent to V. Right? So the degree of this vertex Vi, the degree of Vi only among these vertices Vi, Vj. So let's denote this subgraph. So let's denote this subgraph on the vertices Vi, V2 and so on, V delta plus vertex V. So this subgraph, let's denote it by, I don't know, like, H was already used, I don't know, like J, I don't know. So let's denote this subgraph as J. So the degree, now the degree of this vertex Vi, not in the whole graph, but just in this subgraph. The degree in this subgraph J of vertex Vi, of any vertex Vi, is already equal to delta, because it is adjacent to delta minus 1 other vertices from V1 to V delta and to vertex V. So the degree is already delta, but recall that delta is the maximum degree. So delta is the maximum degree of the whole graph, like in graph G. So it means that this vertex vi, it cannot be adjacent to any other vertices in the graph J, in the graph G. So it follows from this that the degree of vi, and this is for any i. So the degree of vi in the graph G, in the original graph G, is also delta, because it cannot be greater, because delta is the maximum degree in the whole graph. So for any I, so vi is not adjacent to any other vertices. Is not adjacent to any other vertices in the graph. Vertices in G, except in this subgraph. But then, like, since the whole graph, so, and this is because for any I, right? So this subgraph basically, and V also is adjacent only to these vertices V1 through V delta by definition. We defined those vertices V1, V delta as those adjacent to V. So therefore, J is not connected to any other vertices. The whole subgraph J so it follows from this that J is not connected to any other vertices in G. But the only possibility when this can happen is when there are no other vertices in G, because the whole G is connected. So by the statement, in the original statement of the theorem, we assumed that G is connected. So because, so it implies, so from the connectedness of G, it implies that this subgraph J is the whole graph G. There are no other vertices in the graph, right? Because G is connected, and we established that J is not connected to any other vertices. Therefore, there could not be any other vertices. Because if there were, the graph G would not be connected, and it is connected by the condition in the statement of the theorem. So, but this implies that J is equal to G, and therefore G is actually K delta plus 1. Because if you look here again, so we concluded that the subgraph on the vertices V1, V delta is K delta, and this whole, and V also is connected to all of them from V1 to V delta. So this subgraph J is K delta plus 1, is the complete graph on delta plus 1 vertices. So this whole, the whole graph is then a complete graph. And for a complete graph, we don't need to prove anything, because a complete graph is the exception from the upper bound. So this concludes the proof of the theorem. So again, like, we didn't prove that any graph is a complete graph, because we proved it under the assumption that we could not extend the coloring from G minus V to V. So under this assumption that the coloring could not be extended from G minus V to V, so the step of induction does not work. From this assumption, we proved all these claims, and ultimately we proved that the graph is a complete graph. So the only case when we could not extend the coloring to this additional vertex is for a complete graph. So, and a complete graph is the exception. So this concludes the proof of the Brooks theorem. So the proof was quite complicated. I think it was the most complicated proof that I made a video so far. So that's it for this video.